All right, it's the day before an exam. We have a review period today, exam tomorrow, an assignment due next Wednesday, a project due next Friday, and a final exam over finals week. I think that's Thursday. I can validate that to be absolutely sure and give you I've actually looked at the schedule more recently than I'm relying on my memory for. The more I live, the more I realize my memory is very unreliable. Questions before diving into the review? All right, we want to start with going over this question in the last couple, or do we want to start with questions and then dive into this as we have more time? Nobody has an opinion.
I think my questions will get answered, man.
Well, you know the questions.
Yeah.
It's your go. I don't know questions.
See, if you put all the power in my hands, I'm not going to give you anything. This is what questions are for. So that you can word them in such a way that I will reveal slight pieces of information or pieces of information that will help you.
Well, I already know this in one question.
Yeah.
It's the best.
Ask vague questions, get vague answers. Or ask questions I can't reasonably give you the answer to, get joke answers. What concepts can I help people better understand?
Are we doing countability, I guess? Like we have to come up with a function.
Maybe.
All right.
Yeah.
For a question like this, it just says a non-deterministic. If it is, one that's like a two-tape or like a one direction one, is that okay for a question like this?
Yeah.
You have to.
Yeah, you don't. If you are given the ability to use more power, you do not have to use all of that power. But usually, if that kind of power is given, you might want to question, why am I allowed to use that? You might be making life harder on yourself. You allow for non-determinism and try to answer the question deterministically, even if you think you have an answer for that. It was probably designed to utilize that non-determinism in some capacity. If it says you may use multiple tapes, that means you probably don't want to consider a solution on one tape.
Yeah, because for this one, it just says a non-deterministic. So I was like, okay, maybe it'd be easier if I
Yeah.
That's one question. Are there going to be questions that say like use one tape?
Maybe.
Like English choice social instead of using one okay.
If it's completely trivial to do on two tapes, it's incredibly trivial, then I would restrict you to one tape to make sure that you know how to manipulate a Turing machine. But if it's not incredibly easy with any particular setup, then I will probably say you can use any setup that we have proven to be identical to the base Turing machine. Because I don't like restricting people unless it is necessary to get across the learning. Other questions? Yeah. Yeah, actually, on the very next slide, the very next thing that is here is going to be countable and uncountable sets. So if we still have some questions at the end of those examples, I'm happy to circle back, answer further questions, think of some additional examples, etc. But yeah, let's get those two out of the way and then circle back. That's a good question. What type of questions would give the instinct, oh, I should use multiple tapes? It's a really good question. From my perspective, whenever you're doing something independently, or you need to parse part of one tape at a time. So one of the examples for this was determining the exact one, I guess, that's on here on composite numbers. You're going to figure out if 2 is a divisor of the number, if 3 is a divisor of the number. And as you do that, you're going to be moving piece at a time through tape 1. And how you know you've reached that piece is you fall off the end of tape 2 and then reset tape 2. If you're going backwards and forwards and backwards and forwards over a string, some number of times, a second tape will help to recognize when you have reached the end of that part. So if you're dividing your string up into pieces, I would say use a second tape to recognize those pieces. If you have a two-dimensional problem, you may want some kind of two-dimensional tape where the tape has an X and Y coordinate, and then treat it more like a discrete coordinate plane. Yeah, whenever you want to break the problem down into components, you can represent those components on a second tape.
And in these, are we assuming that for example, for this one, if it's a 2-tape Turing machine, that the first tape has the number in unary form and the second tape is empty?
Yeah. Yeah, that is exactly how you would want to start.
Okay, just wanted to make sure.
Yep. Yep. Other questions before we think about a solution to this and go into accountability and uncountability? Okay, if we finish these couple of questions, I'll circle back and ask questions. And if you've thought of questions in the meantime, then I'll be happy to field those as well. How did this go? Anyone work on this between yesterday and today? Do we think we have a solution from this from yesterday? Who would like some more time to work on this right now and see if we can come up with a solution in real time? Some people, let's do that. Let's spend a little bit of time working on this, and then I will ask for a volunteer to come up and volunteer their solution and describe why they think it works. Are we allowed to use Hull on a tape? I'm not sure what you mean quite by that. We have blanks. Blanks signify that something is empty, but halt is something that we do from states. So usually when you, stop moving. So you can use the stay. Since we showed that a stay move is equivalent to a left and then a right, or a right and then a left. But there is no transition that says stop moving and you can't start again. You just have to get in a loop of stay transitions. How are we doing? We feel like we've at least been able to get started on the problem. How's it going? Yeah. It's a bit of a challenge. We're looking at the steps of this. Here's what I'm thinking if I'm writing. Here's my logic for the problem. Written in second grade handwriting. There's still an edge case this is missing, but that's okay. Yeah.
Same terms.
You don't, but if you're going to, you're gonna verify and then you have to reset to add the next one, so it just kind of becomes a verify, then add, then verify, then add, which is going to, it just makes it a little bit more complicated. If you're allowed to use non-determinism, then you can take the concept of resetting and then adding one and turn that into just add one. So it takes a chunk of the state machine and just turns it into a loop.
Yeah, because I probably a couple extra states.
Mhm. Yeah, so if I'm gonna give something complicated like this on an exam, I'm probably seeing if it can be simplified with non-determinism, phrased as a non-deterministic TM, and then allow you to use non-determinism so that it's not quite as intense in the exam setting. Couple edge case issues with this. If we're looking at this, what are the edge cases, or what are the checks that I'm not making that I need to? I think there's two of them. Yeah,
How do you know if you've gone through enough numbers that it's greater than the number on the?
yep, that's one of them. So I think when we non-deterministically set up the next tape and add one, there's a small verify that says, can I move right on tape one? If I can move right on tape one, see a one, move back left, continue. And that creates the termination condition from here. If we've set up a thread and we can terminate the setting up the next thread and terminate that non-deterministic process of creating that once we see that. What's the other? Yeah.
I don't know.
Is the last case you covered if you fall off the first tape and there's still numbers on the second tape? Can that happen?
That can happen, and that would just tell us that the number is
Or
not composite, or it's not. At least that thread is not composite. But yeah, I think the one remaining issue here is that it will tell us that 2 is composite.
oh,
We need a very special case for that, because as soon as we set up the tape with 1, 1, it's going to verify 1, 1. Hey, it goes in. Although maybe a special case of when we set up that tape, look and see if we can move right on tape 1, maybe that would catch that. Anyone have something approaching a level they think they'd want to draw for this? It's probably not worth the remaining time to get to that point and then draw it out. I kind of want to go to countable and uncountable for a bit. This is something we can come back to again if we have time for that. This is quite the challenge problem. I would hesitate to throw this on an exam, but if I did, it would be the last question, the challenge question, come up with something close, get some partial credit. There's quite a bit to think about here, but I did want to at least have an instance of non-determinism and how to build non-determinism into Turing machines in these practice problems.
don't think I have any to actually write it, but I guess the idea I was thinking of was you would have a second tape and you would essentially just pick two arbitrary numbers that are both at most, half the value of the value of the first tape,
Okay.
and then multiply them. So you essentially just find two arbitrary values to multiply. And if you can multiply these two arbitrary values and get what's on tape one, then you have something that's
Okay, and then you could iterate through all
yeah,
combinations
you
of,
can iterate through
And then this is it.
that would work. All right. Here's a question, reasonable, that I might ask on an exam. Set of all finite length binary strings, is that countable? If it is, determine a procedure for enumerating them. I'm not sure if I know what you mean, Jimmy. Why is there at least one tape surrounded by blanks, some stuff in between the blanks? What do you mean by does not begin and end?
Table for this.
Maybe.
It's just, I guess my logic, I don't. Is that, can't you just find an index for each binary number? Like every binary number is a number. Right?
Are there any finite length binary strings that are equivalent in number? So technically, 1 and 0, 1
Right.
are different binary strings, but if you were to query something like, do these have the same value? I don't know, do they have the same value?
Yeah, but 0 is like not there. You know what I mean?
It
I get what you
is a
mean.
number,
Yeah.
yes, but as a binary string, they are distinct. We don't mean a binary number, we mean finite length binary strings. In which case, these are two very different strings.
The enumerating this similar to like previous one we did before, where we just take lengths of 1, lengths of 2, lengths of 3.
Sure, how could we map that to either the positive integers to get an index to it? What process would we use we need a procedure for enumerating? So I guess the enumeration procedure would be lengthwise. That would probably be good enough. But it would be nice if we could have a function for going between strings and numbers or numbers and strings. In an exam setting, I probably wouldn't ask you for the function.
When we say
What would that look like?
When we say finite length, does that mean if we had 0, 0, 0, 0, 0, 0, 0, that it would end at some point and we can move on
Yes.
to the next one?
Yeah.
Okay.
Yeah, there are no numbers that go on forever.
Okay.
So yeah, a procedure for enumerating them would have all length 1 bit strings. We would have all length 2 bit strings. length 3. Did we do it? Any thoughts on that? One thing to recognize is that there are going to be some power of 2 number of each length. So we start out with, we have 2 to the first, length 1. We have 2 squared, length 2. We have 2 to the third, length 3. So wherever it is that we start this process, the number that are going to be before that is capped, or we know that it's going to be, if there are 2 to the third of this, there's 2 squared plus 2 to the first that come before it. So we can set that as a baseline. And then from there, we add the value in binary. So we can split it up into 2 components. Kind of the baseline of the sum of all of the powers of 2 that come before it. And if we know the sum of the powers of 2 that come before it, since that is the case, then there's a constant time way to figure that out as just the power of 2 that comes next, minus 1. So we could do it. Again, in an exam setting, the more important thing for you to make sure that you write down is that there is a process to do it. That you would say that we write all of those of length 1, length 2, length 3, length 4, length 5. For each length, there are going to be twice as many as there were before, but twice as many any number of times never becomes infinite. There's always a finite number of each length, which means that this process will eventually reach any number that is a query. If I give you a 17,000 digit long binary string, we could eventually get to it with this enumeration procedure. That's going to be enough in an exam setting. If this were a homework question, I'd want you to come up with a function. Questions? So this is enumerable. How about infinite length binary strings? So now we don't even care about the finite length binary strings anymore. We want to enumerate the infinite length binary strings.
But I'm like really confused because when we're doing it in terms of size of the string, doesn't it not matter? Like whether it's infinite or finite. It'll just keep going. Like I just don't understand the wording here.
So an infinite length binary string is one such, either that there's a pattern, you could specify that here is the pattern and that pattern repeats forever. Or it could be that there's some sequence that never repeats, kind of like pi is a real number. It is one of those such real numbers. If you wanted to ask what are all of the infinite length real numbers between 0 and 1,
Oh,
we could specify that that is a set of numbers. We would never be able to state what some of them are because they don't repeat, but we could state what some of them are. The rational number 1/9 is a real number that is infinitely long. And it has some representation that we can at least grasp. There's a numerator and a denominator, so it's rational. But imagine trying to come up with the set of all infinite length binary strings. All numbers that don't end for some reason. So the string of all zeros that goes on forever. The string of all ones that go on forever. The string of infinitely repeating 0, 1, 0, 1, 0, 1 forever. 1, 0, 1, 0, 1, 0 forever. 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0 forever.
can we just say no?
But why? Yeah, come up with an argument based on what we've talked about in class as to why that wouldn't be countable. Yeah.
I would think using the diagonalization, we would prove that this is uncountable.
Cantors?
Yes.
Yeah. We actually want to attach ourselves directly to Cantor's diagonalization for this. So we would have this list, it's a proof by contradiction, say that they were countable, then here are all of the numbers infinite between 0 and 1, not between 0 and 1, between there's that are infinite binary strings. We're going to write them all such that there is the first digit, the second digit, the third digit, the fourth digit, etc. on forever. And all we have to do is come up with a number that's not in this table. And so we're going to take the first number, whatever is in this first spot, we're going to invert it. Whatever's in the second position on the second string, we're going to invert it. Whatever's in the third position, third string, we're going to invert it and continue that process down the diagonal as we build this number. And this is a procedure for creating, this procedure would not stop, but we would be creating a number that is not in this table. A binary string that is not in this table. So this table cannot be complete. That is exactly what we want to do. Questions on using cantors for a problem like this? Okay, let's go a little bit more abstract. How about the set of all languages that are not recursively enumerable? Are those languages countable? To remember to not be recursively enumerable, a Turing machine cannot answer yes in a finite amount of time necessarily. There's at least one string for which the Turing machine would enter an infinite loop before answering yes. It's recursively enumerable if we allow it to go into an infinite loop to be able to answer no. But to be not recursively enumerable, we can't necessarily answer yes, that a string is in the language in a finite amount of time.
Before you even get into indexing, how would you order them?
That's a good question. We didn't necessarily have a way of ordering the infinite length binary strings. We just knew that by contradiction, we assume that we can order them. Can we make a new one? And that's kind of how we show that something is not recursively enumerable. So could we use something similar, some similar idea here? So assuming they are countable, we have a list of all recursively, non-recursively enumerable languages. Could we generate another one that is not in that list somehow? You could also attach yourself to exactly that line of thought. How could we list them? Could we use a Turing machine to figure out what those languages are? If they're countable, then we need to be able to do that. In order for it to be countable, we need a Turing machine that can generate that set of languages. How would we do that?
So you could potentially do it by the number of order them by then, or at least starting with the number of transition functions.
The way that I'm going to do this, I've never seen a textbook do this, but the way that I'm going to suggest is just thinking outside the box a little bit. There is a non-recursively enumerable language for every set of real numbers between 0 and a real number between 0 and 1. So for every real number between 0 and 1, that represents the endpoint of a non-recursively enumerable language. Does that make sense? That's an infinite number of non-recursively enumerable languages. So we would have the set of all real numbers between 0 and every possible real between 0 and 1. Every possible endpoint that we could here. And if this set of languages was countable, then the reals between 0 and 1 would be countable.
But they're not.
But they're not. So there's no way to represent this subset of the set of non-recursively enumerable languages. So even when focusing on a subset of this, we have a way of saying that this isn't possible. So it doesn't need to be particularly fancy. Just coming up with some kind of outside of the box solution like that would be able to answer something like this. Frequently, proof by contradiction, or just thinking of the world in terms of a proof by contradiction does you well in this class, at least. Think about, well, if it were possible, what else could I do? And that becomes kind of like a reduction in the ways that we were talking about reducing to the halting problem. This becomes a reduction to a non-recursively enumerable language. Trying to count non-recursively enumerable languages reduces to a non-recursively enumerable language.
As a potential counter to that, can a language that is not recursively enumerable be represented as a finite binary string?
I don't think so.
So it would be an infinite binary string.
Yeah, it'd be more like an infinite binary string because it has an infinite number of elements to it. If it had a finite number of elements, then you could represent it as a finite binary string. And then you could start to enumerate that and place the different languages and map them onto that.
Then
But
the same proof for the previous Turing machine just applies, just to see
yeah,
if we.
you could go down that route. I like that one too.
So could I just do a diagonalization where I make like a piecewise function? If I have a 0 at the nth character, I change it to a 1. If it's anything else, that like any symbol ever, I can change it to a 0. The resulting binary string is not limited.
Yeah, I think you could do that too. So yeah, lots of ways to think about this. I, when possible, like to generate open-ended questions like that make you come up with a way of thinking about it that works, and there are multiple right answers. But just whatever makes sense to you, tying it to something that we've seen before in this class, or even if it's not in this class, something that you've seen before. Last few minutes, any other questions on countability or anything else off the study guide? Hopefully this was helpful. So we know that recursive languages are countable, recursively enumerable languages are countable, but non-recursively enumerable languages are not countable. And so the set of non-recursively enumerable languages is also not recursively enumerable. So they also can't be counted. For recursive languages, you're going to make a generator Turing machine and a verifier Turing machine. For recursively enumerable languages, you're going to use diagonalization. You're going to run the first transition on the first string, the first transition on the second string, the second transition on the first string, etc. And that's how you can show that recursively enumerable languages are counted. How are we feeling? We look more defeated than when we came in this morning.
Yeah.
I don't like that.
I feel less defeated.
That's good.
I feel like I understood it now so much.
Interesting.
I feel like because in the other languages and like all the other definitions, we've done a lot of examples. Like for regular languages, we had a lot of examples kind of
Yeah.
working with them. Here, we kind of almost like brushed over a lot of stuff. And because of that, it feels very arbitrary sometimes. Because you understand the definition at a very high level, but getting down to that really solid grasp of what you're talking about makes it a little difficult.
Yeah, it's like I feel like I understand the intuition, but I don't think I could create like a mathematical construction or a function to show something recursively or the word. Other than by like just making like a order that I could like draw on a table, right?
Yeah, that's probably the extent to which I would ask you on an exam. When you only have an hour and I have to ask you more than one thing in that hour, I can't target something that's going to be a long, drawn out process.
Okay.
That's why I asked the homework questions. I asked those on the homework. So I think knowing the basic idea of being able to recognize languages that are recursive, recursively enumerable, non-recursively enumerable, be able to do that, and then be able to talk about how to enumerate the classes of languages that are enumerable, and why it's not possible to enumerate a class of language that's not recursively enumerated. That's about the level of depth I can reasonably go into. Other last minute questions? What else can I do to make you confident or set you off on the right foot going and studying or coming to office hours? Right. We can continue this conversation in office hours.